Hey everybody, how's it going? It's Obi-Wan Pez for Simplex Pachinko. We are going to be doing some math tonight, so anybody who has any questions, please let me know what they might be, and we will get to some good stuff. If this is your first time in, we do have a list of other math-type streamers. We have Dawn Does Math, Zach at e to the 2i pi, Penn Center, Ian Stuckey, Obi, which is myself, and Simplex Pachinko. Dan is Danny Highway, and Dr. Gold at Actual Education. So if you haven't been at any of their streams yet, please definitely check them out. Really great bunch of people, and really want to help out. So if you have any math questions, we usually have I'm usually found at Penn Center's Discord server here called The Elements. We are kind of informally The Elements crew. And we do a bunch of our math help out of there as well as out of each individual Discord server. I don't actually have my own, but, you know, that's fine. I'm not too worried about it. I hope everybody's having a good start to their week. Started out by streaming yesterday. Did some... what were we doing? Euler project. So doing some learning of Python, trying to get our knowledge back up in the first place. Alright, so I think that we're going to start with maybe a little bit of our usual specialty here, differential equations. Let's just turn to a random page here. Oh. That was maybe a slight mistake, but that's fine. It's fine. So find the Laplace transform of... I actually looked at the other side of the page there, which looks pretty nasty, but it's also a completed problem, so it's not that bad. Alright, find the Laplace transform of the following. So we're going to do f of x is equal to x times e to the bx. Somewhat implied by the statement itself, f of x is equal to a function of x. Since b is not part of the function called parameters, it's going to be a constant. So, okay. So if we're going to find Laplace transforms of any particular function, it's helpful to remember what a Laplace transform was. So, no, Joseph Louis was Lagrange. What is Laplace's name? That's a very good question. I don't remember. Pierre-Simon de Laplace. So Laplace was also, I think, backtalk to Napoleon. wasn't the one. Okay. Hmm. 11th of December, 1797, Napoleon Bonaparte dined with some influential members of the Institute. Institut of Sciences. Where is it? Well, I'm not finding it immediately here. Anyway, members of the Institute to ensure his election which was to take place 2 weeks later to show off his mathematical skills. Napoleon explained to Laplace, the so-called French Newton, how to find the center of a circle if you only had a compass and no ruler. Laplace would have exclaimed, "We expected everything from you, General, except lessons in geometry." Interestingly, did Bonaparte mention that this geometrical construction was, in a way, a war prize, since he had obtained it from a Milanese mathematician named Mascheroni, whom he had just met during the Italian campaign. Perhaps it is what convinced Laplace to vote for Bonaparte. Could have been fun. Hey, maybe this guy's not such a dunderhead after all. Merriweather, how's it going? B is not required to be less than 1. It is just going to be a constant. So, because we're doing Laplace transform, we don't really actually care what B is. The transform itself... Been a while. The transform itself, by Pierre-Simon de Laplace, was to say that taking this particular transform, which everybody else named the Laplace transform after him, and yes, gave it the capital L as its signifier after him. After it started becoming popular and useful, we have the typical notation is to take f of x and we transform it using... I need to boost this, otherwise I'm going to completely blow out my shoulder. Or like lean way over. I don't like that idea. Alright, there we go, much better. Yeah, also true. Okay, so typical notation is to say that cursive L Laplacian of, using brackets, f of x is equal to capital F of s. So we're using s as a dummy variable, which is then used in the definition, which is going to be equal to the integral from 0 to infinity of e to the negative sx totally times f of x dx. Yes, I'm not kidding. They decided to use that. I always get a couple of Snickers out of my students. And if you don't like that particularly, you can also say, okay, well, this is going to be the integral from 0 to r, where we take the limit as r goes to infinity. So if you are completely offended, by the use of a limit, by the use of an infinity symbol, you can say, okay, well, we're just going to do a limit as r goes to infinity to get that. Thank you very much for the follow. If you like tonight's stream, and thank you for the follow as well. If you like tonight's stream, feel free to tell your friends. Get some cool stuff going. And if you do have any question, Agent Ulsri, Absolute Balderdash, well. So for whatever reason, the Laplace transform became one of the ones that was actually like extremely helpful and useful. And I'm not going to say necessarily immediately why it became so useful, but nonetheless. Yeah, kids these days in their infinity. Very true. It's like saying infinity plus 1. How dare you? Okay, so in doing the Laplace transform, what we're saying is we want to take the Laplace transform of x times e to the bx. And this is going to be f of s in this particular case, which is equal to integral from 0 to infinity. Yes, I will use the shorthand. Times e to the negative sx times x e to the bx dx. Alright, so the good thing about this one, yeah, I'm kind of in the way there. Oh, hello, spider. Good thing about this one, part of it will simplify a little bit nicer. Alright, integral from 0 to infinity of e. Now in this particular case, what we get is that the e's will combine, and we get a negative s plus b, parentheses, times x dx. Okay, so we're going to hang on to this for a bit, and we're going to say, well, we don't know exactly what's going to happen with all the little individual pieces, but in order to take this integral, this is actually doable. What we can do is say that this is going to end up being a integration by parts for how we did this in, much earlier sections of calculus, usually Calc 2, I think. Yeah, Calc 2. So what we say is, okay, let's let u be the thing we want to derive. That's just going to be x. And therefore du is going to be dx. dv is the thing we want to integrate, which an e function is going to be very nice to integrate. Negative s plus b times x dx. Right, and then going backwards, what's the actual integral of this one part? E to the x and e to the negative x. Yeah. So when we bring them together, it makes only one term. So okay. So here we still get the e to the negative s plus b parentheses x, multiplied by, here in this case, the constant is going to come down from up top. The way that this really works, the way that I actually write this when students are learning this section, like any of the constant multiples and things like that, taking integrals, is that, well, we needed integral of e to the u du. And we don't actually have that technically. So what we need to do for this is say that we need, right, u is equal to negative s plus b times x. This is all constant. Oop. Just going off the page, it's fine. That bit up there is a constant. So what we need to make this super easy, right, e to the u plus c, is to have e to the negative s plus b parentheses x times, what's the derivative of that u thing? Well, it's, again, constant stays where it is, negative s plus b times, now instead of x, we take the derivative of x, it's dx. So that's what we need, but we don't actually have it. So what I usually tell students to do is to say, okay, we have, in this case, the integral of e to the negative s plus b parentheses x dx. And we need that constant. So make it negative s plus b over negative s plus b. Take the one on the outside and move that in so that we end up getting this exact thing, 100%. That then leaves the negative s plus b on the bottom. And that's where that always comes from. I tend to like placing those in so that people can know like where this stuff comes from. It's not just some arbitrary weird thing that, well, I have to follow this rule. Okay, why do you follow that rule that particular way? Well, my teacher told me. Right? That is the absolute worst explanation. And if you have to fall on because my teacher told me, you don't really understand it. And so that's like my main driving force for all of this, is to make sure that you really understand where these things come from, why they exist, that there is an actual reason for all this stuff. Okay, so we've got now, we take the, nope, it's uv, right, x e to the negative s plus b times x minus, so uv minus integral of v du. So 1 over negative s plus b e to the negative s plus b parentheses x multiplied by du, which is just dx. Okay, and now we do have the exact integral that we needed up top, or that we had up top. And so this is just going to become x e to the negative s plus b times x. And then here, right, we're going to get the exact same thing. No, sorry. We don't have the integral. Jeez. Sorry, no. We don't have the integral. We have a 1 dx on the top. So we have to do it again. And this is going to multiply a second negative s plus b to the bottom of this term. So we got 1 over parentheses negative s plus b squared e to the parentheses negative s plus b x and plus c. But in the realm of Laplace transforms, I don't think we end up, no, we don't end up with the constant here, because if you end up reversing the Laplace transform, you're taking a derivative, and so it knocks that off there. DiffyQ professor taught this, yep. Engineering professors always expected you to know it. Yes. Yes, they do that. Like, You guys passed differential equations. You don't need to remember anything anymore. Okay, so Laplace transform of xe to the bx is going to be equal to, we already got the equality sign in there, fine. Okay, it's over my head. Now it's beyond that thing. Alright, so we get these two things here. Oh, and then I forgot completely, this is not dx. All of these. Right. Starting from here on, those are all supposed to be s's. So I just screwed up the entire integral because we're trying to take this in terms of s, not x. It's really too bad because this was actually reasonable. Alright, well, you know, I liked that explanation and stuff, but it was doing completely the wrong thing. You get a little carried away sometimes, and Kjorifgal, how's it going? Yeah, that's true. You can use power series. Most of the time you're not using power series just because you're using trying to find out what the we're just trying to find out what the Laplace transform itself is. So yes, you could go with a like Taylor series expansion, that sort of thing. Yes, this is the nice part. S is a constant, or x is a constant. S is not. Okay, so here we've already we can do the integral now, right? This is the only s that exists in this entire integral, and x is not a function of s. They are independent of each other. So x is a constant multiplied by, again, this is s equals, just in case you forget. Yeah, Merriweather, I have been in this situation many times in front of an actual class, which is somewhat embarrassing. Alright, so in this particular case, what we have is a negative xs in the exponent. And so we're taking a... nope. We need to find out what the derivative of this bit is, right? So u is equal to a negative s plus b times x. Therefore, du is going to be a negative x. And again, this is du ds. The other way that I do this, and in differential equations classes, this works very nicely, is you keep the differential around instead of dropping it to the other side. So du is equal to negative x ds. And in this way, usually you don't forget what your variable is. Kind of helps. Okay. So we end up getting the e to the negative s plus b parentheses x because, again, nothing actually changes here in the exponent, right, for the exponential function itself. But then we do have a constant multiple And in this particular case, this is going to be a actually, that was even silly because we have the x we need right there. All right, and ds. The only thing we don't have is a negative. So in order to get that negative, again, we're going to pop this in here and also on the outside, or -1 times -1 on the outside, bring one of them in. However you want to do it, it's all the same stuff. So what that does now is it says, well, that's not going to be there. Instead, this is just going to be a negative e to the negative s plus b parentheses x. And again, normally you do, oh, wait, this is a definite integral, right? So we don't even have to do that. This is going to be s going from 0 to infinity, which is going to be equal to negative e to the, in this particular case again, if we go like negative r plus b x, okay, minus a negative e to the 0 plus b parentheses x. This is going to end up being a, in this case, limit as r goes to infinity is going to get us a negative infinity up in the numerator. Negative infinity is going to swallow the entire numerator in the entire exponent. The negative infinity swallows the entire exponent up there because it's just addition and multiplication at that point. There's no multiplication by negatives, so we've just got a negative infinity. So negative e to the negative infinity, if you excuse the infinity symbol showing up in the middle. Some people get bothered by it, like I said. So this is just going to be 0. And over here we get a plus e to the, and now the 0 plus b becomes b, it's just bx. Why do I feel like something went horribly wrong? Hey. Because something went horribly wrong. Cool. All right, what went horribly wrong? Well, harumph. Oh my god. Yeah, no. It was on the... Oh my god. No, I copied it right the first time. Yeah. You can tell it's been a while since I've done these. Oh. Yep. Okay. Jeez. Yeah. So we're having an interesting day. It's fine. Okay. All of this needs to be evaluated where x is going from 0 to infinity. I'm really sorry about that, guys. That was... I should know better. But like I said, it has been such a long time since I've actually done these. Most of the time it's table lookups. And because you're doing a table lookup, you're just not paying attention to what things mean. See? This is what I'm on about. Okay, so Laplace transform of x e to the bx is going to be equal to. So in this particular case, we end up with... Yep. R goes to infinity of r times e to the, here, parentheses, negative s plus b times r. Okay. Minus 1 over negative s plus b squared. Yeah, okay. Times e to the negative s plus b times r. Okay, and then this is going to be minus 0 e to the 0. So that's a nice, easy, 1 times 0. There we go. Oi. 0 overall. I shouldn't do that. It looks like 0 over 0. That's fine. We'll deal with it later. And then plus 1 over negative s plus b parentheses squared times e to the 0. All right, yeah. Now, Merriweather, now we need to go back and say, now hang on. Is this going to work for all values of b? And now your answer is, well, not really. Right, now we say, in order to get convergence, we're going to get convergence when negative s plus b is going to be less than 0, or when b is less than s. Right, because we need this thing to come out to e to the negative infinity in order to get these terms to go away. Otherwise, we end up with infinite terms, and we don't like infinite terms being thrown in here. Okay, so Laplace transform of ex e to the bx, where b must be less than s. S is also defined in the other realm here. So, like, Laplace transforms and your standard space kind of look like two different things. So it's a little weird. S is also the variable over which this is working. So, no, it's fine. We're good. Okay, so up top, as long as we have convergence, we've got a 0 minus a 0 minus a 0 plus a 1 over parentheses negative s plus b parentheses squared. All right. Let's make sure it actually looks anything like the other one. Yes. Thank you. Yeah, also watch your links because it got cut off at the end there. It's one of those things, like, it just decides when to end it. Also, this is another interesting thing. Negative s plus b is equal to negative parentheses s minus b, which in this particular case is 1 over parentheses negative s minus b squared. And if we give the square to each parts, it's 1 over s minus b squared times 1. So it's perfectly possible to say, oh, well, it's this too. Granted, that only works with even roots like that, but nonetheless. Or even exponents on the inside. Yeah, well. So you can change it around, generally speaking, because S is commutative on R. Oh, reals, yes. Right, and generally speaking, we do like to put our S's first, just because they're the variables. It's not like it really matters. You can put it anywhere you want in here, as long as it's all, you know, the same communication is happening, and we're good. All right. If anybody has any particular questions in the field of mathematics, or various other things that I'm interested in, what have you, let me know if you have any questions, and we'll try to get to you in short order. Potatoes, hi. let's aspire to write smaller. So, if anybody has any questions, let me know. So this is something called Laplace Transforms. It is a part of differential equations, which is a sophomore level, usually, college class, provided that you're taking freshman level calculus. So, if you are in physics, math, engineering, computer science, generally speaking, you're taking differential equations at some point. At this point, it is kind of like some interesting algebraic manipulation on top of doing some calculus. Well, as Merriweather says, hey, if you got to learn to love this math, and you need to do some differential equations, I will be putting on a differential equations class at some point this summer. I'm trying to figure out exactly when to do that, when we have a good stretch of time. It's going to be twice a week, most likely either a Monday, Wednesday, or Tuesday, Thursday. Most likely sometime during the middle of, well, no. It depends. It's going to depend on who's interested and when, what time zones they're active. It's, I guess, probably going to be like this 9 p.m. British summertime, Western Europe time period. Just because that's the most convenient for me and probably everybody else. But in theory, if we've got enough people who are in the correct time zones for it, we might also do it sometime midday for my time. That would probably be like 7 a.m. Eastern US, 4 a.m. Pacific, or something ridiculous like that. Or, like I said, we've got here 9 p.m. British is going to be 4 p.m. Eastern and 1 p.m. Pacific. So we'll see when everybody's interested and follow that. I'll be back in, let's do 1 minute. And just hang around. Thanks very much for coming. Be right back. Yeah, so common occurrence on this stream, we have somebody who will come in from time to time. This is my spouse saying goodnight. Occasionally we have small people who decide that you know, they're old enough now. It's not a weird problem. Fourier transform, nice. Yep. This one is Laplace. So Laplace transforms, generally speaking, are used to do difficult integrations, and by making it a different kind of function, it makes it super simple to actually do the integral of this particular thing. So what we've done here is we said if we were trying to take the integral of x e to the bx dx, and we were having problems with this for whatever reason, we could instead make this the integral of the Laplace transform. And actually that would now be ds. So that's how you're doing that one. Which would then produce a different result. So instead of I'm sorry, hang on. Yeah, okay, not exactly. Sorry. This one's not for difficult integration. Fourier transform is for difficult integration. This one is for saying, I can't solve a differential equation. So we end up with something like, you know, y double prime plus 3 3y. Let's see. Yeah. Oh. Okay, I get it. We're good. Let's do, let's see, 3y, 3 and 1, no, that's not right. 3y prime, we'll make this, make this 7 and minus 4 to get positive 3. So multiply those together, we get a negative 28y is equal to x e to the bx. There we go. Okay. So I did this intentionally just to make an easier problem on the left. This is actually not too bad. So what we do is we say, okay, we're going to get this thing on the left here. If we want to take a Laplace transform of all this stuff and the Laplace transform of all this stuff, on the right-hand side, we get that thing that we found up there, which was 1 over s minus b parentheses squared. On the left, what we have is a differential equation that breaks down the Laplace transform of y prime and the Laplace transform of y and the Laplace transform of y double prime have this nice little scheme that works out. So the Laplace transform of y we're just going to call y, and it's on the variable s. Y prime, if we take the derivative and put it into the big definition that we had up top, it ends up being, this is 1 over s times y of s, and second derivative ends up being 1 over s squared y of s. Right. So then the left-hand side of this, the former differential equation that's up there, ends up becoming 1 over s squared times y plus 3 over s times y. Did I mess this up, or is this good? Oh, yep, okay. I only messed it up slightly. That's better. It's not 1 over s and 1 over s squared. It is, conveniently, just s times and s squared times. Oy. So we get s squared times y plus 3sy minus 28y. So this is going to be y times the quantity, here s squared plus 3s minus 28. We've just taken a differential equation and we've turned it into basically an algebra problem. So our y function, which is a function of s, is going to end up being 1 over a product of s minus b squared times, and we figured out from up there our factors. This was going to be a nice quadratic. It is going to be s plus 7, yeah, and s minus 4. Right, so this is now the y function, and it is in this like Laplace transform land. So now we need to get it out. So in order to do that, we need to get all of these pieces to become the exact same thing that they would have been in like a standard Laplace transform, but separate from each other. One of the things that I kind of glossed over it up here, I should have probably done a little bit better, is that the Laplace transform is a linear operator, which means that because we have this y double prime plus 3y prime minus 28y, we are allowed to break out anything that is added or subtracted and has a constant multiple. So this ends up being the Laplace transform here of y double prime plus 3 times the Laplace transform of y prime minus 28 times the Laplace transform of y. And again, given that the separate things were given over here on this side, we could substitute those individual things in. It's not super easy. Apologies. It's just one of those one of those things. So if you practice and go, okay, I'm going to take the Laplace transform integral, and I'm going to do it with this particular function. I'm going to do it with y. I'm going to do it with y prime. I'm going to do it with y double prime. I'm going to do it with some random off-the-wall function like xe to the bx, like we did up above. Figure out what works, what doesn't. What do you get? So now we got this thing. Our capital Y of s is equal to 1 over s minus b squared times s plus 7 times s minus 4, all in that denominator. We don't have any inverse Laplace transforms that'll just get this for us. You could plug it into like Wolfram Alpha or whatever and get an answer, but the question then becomes, well, how do you do that? How do you undo this thing? And that's hard. It's quite hard. So what we do is we say, okay, we need to get each of these things into their own terms. So if anybody has done partial fractions, this is where this comes in. So with partial fraction decomposition, what we're going to do is we're going to say, okay, if we have something that is 1 over a times b, we're going to get something that is a constant. Let's do c1 divided by the a part plus constant c2 divided by the b part. And we could say that, hey, this is going to work like no matter what. No matter how we do it, it's going to work in some way, shape, or form. So for right now, what we're going to do is say, all right, we need all of our pieces from y, capital Y of s, to be 1 over the first part, which is going to be s minus b squared. And in fact, right, we don't know it's 1. We're just going to call it a. Let it be a constant. Plus b over, this is fine, s plus 7 plus c over s minus 4. Now there is a problem. And that is that we have something here that's going to only give us, at the moment, it's only giving us a constant divided by parentheses s minus b all squared. So, like, what happens if what happens if we add up a certain amount of other stuff and it ends up becoming s minus b over s minus b squared? Well, that would divide out. And then we'd be left with something over s minus b. That's not reflected here at all. So what we need to do is say, there's the possibility that whatever we've got on the bottom, because it has a power of 2, it could be reflected in 2 different ways. One is that it could be reflected linearly, and it could be reflected through a constant. So we're going to get rid of this stuff here just for a second. Nope. Okay. This is fine. Oh. Oh yeah, that was just doubled up. It's fine. Now you can see how all my handwriting comes together. Alright. Or doesn't. Okay. So when we move all these pieces, right? This is what we end up getting. So we get this linear form of a times our variable piece divided by that same variable piece squared, plus b over our variable piece squared. Right, and this could have been, if you'd wanted to instead, a over s minus b plus capital B over parentheses s minus b squared. Me personally, I don't care how you do it in terms of, like, if you were my student, they mean the same thing. You will get different values for a and b as constants depending on whether the s minus b squared in the denominator is on both of those pieces, because the a that has that thing not divided out could be distributed in, adds to the b on the constant term, the lowercase, like capital A times lowercase b, is going to be added to the capital B over on the right, and that's going to mess things up if you leave it all together. Right, and then the rest of the stuff ends up with C and D in those locations. Okay, now all of that is equal to the original 1 over, right, s minus b squared times s plus 7 times s minus 4. It's ridiculous. It's fine. Okay, and then what do we do? Well, we're going to take all this stuff and we're going to multiply it all the way across. So take your least common denominator and multiply it to all the terms. So we've got a times the quantity, s minus b, plus b, all multiplied by s minus b parentheses squared times s plus 7 times s minus 4. All over s minus b parentheses squared. Plus c times, this is s minus b parentheses squared times s plus 7 times s minus 4. All over s minus b parentheses squared. Okay, plus d times the same. So s minus b squared times s plus 7 times s minus 4. All over parentheses s minus b squared. Okay, all terms are going... No, that's not s minus b squared. Man, I'm okay, I promise. Denominators are different. So under c we have s plus 7, and under d we have s minus 4. Glad I caught that. Okay, so then what we have is individual terms end up dividing out from our common multiple, which we multiplied all the way across. Right, and all of that is equal to just 1 on the right hand side, which now I'm moving over to the left, not to be at all confusing. Hello. Here you. How are you doing? Kanya, how's it going? I will take requests, so if you have any questions that you would like to work on here, then we can discuss. I'm just doing a bit of differential equations, so we'll interrupt as you get your questions into chat. Just had a test. Yeah. A times s minus b plus b, other b, times s plus 7 times s minus 4. Plus c times quantity s minus b squared times s minus 4. Plus d times the quantity. Doesn't really matter, right? S minus b squared times s plus 7. S plus 7, not x. Yes, so my recommendation is to post it in Penn Center's Discord under the Math Chat section or the Math Forum section. I can go to either of those while on stream and make sure that like nobody else is messing around with it. And these are also the other math chads who are part of this the elements Okay. So we have Dawn Does Math, we have Zach at e to the 2i pi, Penn Center, En Stuckey, myself, Obi, at nsimplex pachinko, Danny Highway, and Dr. Gold at Actual Education. Generally speaking, we are going to be on stream 1 to multiple times a week doing math, and interested in helping people out, trying to understand how things actually work, not just to get y'all answers. So okay. Then what we have here is that this is going to start expanding everything out. Yep. Completely understandable. So if we do this, we got 1 is equal to, here, as minus a lowercase b plus a capital B. No, that's not right. Those are not multiplied together. Plus capital B. Okay, there we go. This stuff is all going to be multiplied by. This was the same polynomial we had earlier. So that's s squared plus 3s minus 28. Plus. C times the quantity. This is going to be s squared minus 2bs plus b squared multiplied by s minus 4. And that last part, plus d times the quantity s squared minus 2b s plus b squared times s plus 7. Okay, and then here we're going to multiply through, so this is going to be a s cubed plus 3a s squared minus 28as minus a lowercase b s squared minus 3a b s plus 28ab. All right, then our last one there, b, is going to be plus b s squared plus 3b s minus 28b. This does sometimes tend to be a long process if you're doing everything by hand, so sometimes a bit tricky there. It's Art Kirby. Hello. Good evening and welcome. My name is Obi-Wan Pez. This is N-Simplex Pachinko. We are doing some math tonight. This is bit of stuff that we're doing by hand in differential equations. And if differential equations is not your particular kind of math, that is perfectly fine. I have spent 15 years teaching everything from basic math / algebra, like pre-algebra, all the way up through differential equations, and I have knowledge going through master's level. Most of that was differential equations based, so I did some partial and nonlinear differential equations. I don't remember a whole lot of it anymore. It's been like 15 years. So, so if you have any particular questions, feel free to drop them in chat or to Penn Center's Discord, The Elements, which we have. I'm going to post that again for anybody who missed it or wasn't here. So, yep, if you're interested, you can drop some stuff in there. Yep. Nice. And always feel free to lurk on anybody's channel, because it does help the algorithms to understand that, hey, people actually want to watch this stuff. All right, plus c times the quantity. This is going to be s cubed minus 4s squared minus 2b s squared. This is negative 2 times negative 4 is going to be a positive 8 bs. So on the left in Discord, you should see a math channels section, and under it there is a maths forum. At the very top, I believe, there's a thing that says new post. You can click that and go in. If you're on mobile, you may have to go to you may have to click it and then hit threads, and it'll pop up with all of the options, I think. Can't remember exactly 100% how it works from that perspective. And I do this all on my desktop, so right, plus b squared s minus 4b squared. Yeah, no problem. right? And plus, we'll pop that down here, d times the quantity. So this stuff is sometimes used in as like far back as algebra 2. So there was one time where we were trying to solve some sort of equation, and we ended up with some gross stuff that wasn't going to work nice. So we ended up, instead of multiplying everything through by a least common denominator, it ended up working out that doing partial fraction decomposition was actually a decent way to go. A. Oh yeah, yep. So with this one, you want to, first part, starting on the left-hand side, you want to work on plugging in that particular substitution and then doing some factorization to make it nice. The way to make it nice specifically, you're going to end up with a few A's that are kicking around that you can change into something much better. And then you've also got a trig identity. For once you get the A's out of the way, you've got a 1 minus a trig function squared. Okay, so yes, there's actually extremely good news. This complicated stuff ends up being super simple if we look at it, at here. So if you know what if you know what derivatives mean, it ends up being a lot easier. If you don't know what derivatives mean, that's perfectly fine. So in this particular case, this could be, for example, that we are engaging a spring mass system. So if we have a spring with some sort of weight attached to it, and we hold it to a specific level and then let go, what this is going to do is it's going to naturally just follow this particular oscillatory pattern. Now, depending on what kind of weight, depending on what kind of spring, and depending on a few other factors, in this particular case, we do actually have a air resistance that's working on this, or at least we can use air resistance as part of all this stuff. I don't generally... Actually, you know what? No, I don't think this one does. Right, because I think we'd need a x that was attached to our y prime. Anyway, so derivatives are rates of change. our y function, in this particular case, is measuring usually a distance from the initial location of our spring mass system. Now, there are a huge number of other applications that this actually works in. So this particular differential equation could be describing a spring mass system, a system that deals with like a skydiver, like air resistance on a particular sky. Not this one in particular, I'd say, but something like it-ish could represent that. This particular system could represent an RCL circuit. So if anybody does like computer engineering type stuff or electrical circuits, that's what this could be modeling. It could be your car's shock absorber system, which is a spring mass system in its own right, but nonetheless. And there's like a dozen other things that I'm forgetting at this point, but the terms on the left are double prime. Let's go with the other one. Our y here is representing the distance that our mass is currently from its equilibrium point, where if we just like let it go for a while or like held it in place and gently let it go, where would it naturally just rest? So that's going to be our like x0, y0, our initial point. Where would it just fall to rest? That's equilibrium. So y is going to be our distance away from equilibrium. Our y prime is going to represent the speed at which this thing is moving, the rate of change of its position. And y double prime is going to represent the rate of change of its rate of change of the original position, or in other words, the rate of change of its speed. How does speed change? Well, that's acceleration. So we have our y double prime, which represents some sort of acceleration force, or just force. Spring forces are accelerations essentially, right? Our force is equal to mass times the acceleration. They're basically the same thing. Our y prime is going to represent velocity, and our y is going to represent distance. So if we use those, just as I stated there, right? Y double prime is acceleration, y prime is velocity, and y is position. Then this particular function, or this particular differential equation, can represent an oscillatory motion with perhaps some damping effects. So with this particular one, I think this is overly damped, where the system is more like your car shocks, where it's going to kind of like, or maybe more like the, I think this would be more like a air compression brake in like the Tower of Terror type things, where they take you up really high in an elevator, they drop you, and then the braking system is based on air being compressed inside of a big cylinder. So it's going to essentially allow you to fall a ways, and then when it starts catching you, it's going to kind of slow you down fast and get you to more or less stop, like, very quickly. Your car shocks are what are called critically damped, which means that it allows sort of a single bounce before it starts really damping the system, and you don't get a whole lot. Only like one, if you hit one thing, right? If you hit a bumpy road, it's just going to keep doing this. But if you hit a single bump, your car is essentially going to like go up and then sink down into the dampening zone, or it's going to like come down and up like that and then back to rest. It's going to allow one kind of major bump. And then you have things which are like the spring mass system, which is underdamped, which means that basically this is operating on friction alone. You have something that you drop the weight and it just keeps doing this for a very, 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 very long time. It just keeps going over and over and over. You would not want your car shocks to do that. You would not want an RCL circuit in your electricity to keep shuffling electricity backwards and forwards through these individual electrical parts, at least not like that much, right? Not in an oscillatory sense. It would start potentially wear out your electronics a lot faster. This stuff over here, normally, if we're just talking about a spring mass system or your car shocks or whatever else, where you just drop the thing and you're done with it, you don't touch it again, that stuff over on the right is 0. What this is right now, x times e to the bx, this is a force that you're actually actively applying to this particular system. So if you had a spring mass system, this is you going like this, like while it's trying to do its own natural thing, which again have these particular zeros of this function. They have a particular behavior that they just naturally do, again, if you just dropped it and let it go and didn't touch anything. That's the natural behavior. You might recognize the word like natural frequency or resonance frequency. That is what the system just does by itself automatically. When you don't have when you have this resonance frequency, that's what's going to either amplify or start taking away from dampen your system. All right, if you apply either a frequency to build it or a counter frequency to damp it faster, right? That's something that you could do with your forcing function. In this case, x times e to the bx is going to grow x over time, but your e to the bx, we talked about this other stuff over here, we want this to cause it to shrink down. So we don't want to keep applying a force to it. What we'd like to have happen, generally, is that you're going to apply a force to it to try to get this thing to slow down and stop all by itself. So that you don't have to keep applying a force to it or just watch it bounce up and down. Or, in the case of an overdamped system, I think like this one, you don't want a shock to be too great to a person who is on your amusement ride. If you do that, you end up like Gwen Stacy in Spider-Man. Right? Head would snap and the neck could possibly break. That's bad, generally speaking. So that's the sort of thing we're looking at. This is all like how to do this particular system by hand using Laplace transform. So a Laplace transform is saying like, I'm trying to solve this problem. I'm not actually able to solve the problem directly. This one actually isn't too bad. We're just manipulating it because we want to do Laplace transforms. And then after we apply this, how do we then solve it? Yup. Yeah, not that Gwen Stacy, the other Gwen. Yep, that one. Alright, so in this particular case, what we've got now is we would try to rearrange this whole mess of stuff into pieces of like terms. So we're going to look at our s squareds and our s squareds, our s cubeds and our s cubes, our s's and our s's, and our constants and our constants. Some of these things are not constant as far as you're all usually concerned. You know, big B and little b aren't actually constant, or they're constants in their own right, but we're going to use them here to try to figure out what they are. So in this particular case, we're going to get 0 s cubed on the left is equal to a s cubed plus cs cubed plus ds cubed. Right, so we're taking this s cubed here and these two s cubes over here. And we're saying that the stuff that has s cubed in it needs to be the same on both sides of this equation. Or they need to sum up to the same thing. Okay, so what we're going to do is we're going to decompose this entire equation into multiple lines. The reason that we do this is because all of our s cubed stuff needs to be the same, all the s squared stuff needs to be the same, all the s stuff needs to be the same, all the constant stuff needs to be the same. Why? Because this needs to work for all values of s. Right? From negative infinity to positive infinity for s, we need this to work. So it needs to be independent of trying to find a solution within all this stuff. All right, so 0 s squared is now equal to, we've got a 3a s squared minus a lowercase b s squared and plus b s squared. Then we move over. All right, then c, we need a minus 4c s squared minus 2c lowercase b s squared. Okay, plus 7d s squared minus 2d lowercase b s squared. All right, all that stuff is the s squared equation. And then we go to 0 s's, and we do the s equation. So that's going to be a minus 28as minus 3a lowercase b s plus 3 big B s plus 8c lowercase b s plus big C lowercase b squared s plus, this is going to be a minus 14 big D little b s plus big D little b squared s. Okay, now we got something that's slightly different. The constants. On the left-hand side, the constant is 1. On the right-hand side, the constants, i.e. those things that don't have s's, are going to be a 28a lowercase b minus 28b, big B, followed by a minus 4b squared plus 7b squared. Now we do technically have a problem here because we've got a lot of lowercase b's and we've got capital A, B, C, D, which means that we're not going to be able to solve this entirely. We'd want lowercase b to technically still be a variable. It's going to be used inside of all this stuff. No, sorry. We want lowercase b to still be a constant, but now everything's going to be in terms of that constant value. So, it's not really going to work, but yay, good job. Alright, so the way that we normally do something like this is to break it up as linear algebra. And so what we'd say is we've got our s cubed, s squared, s, and constant. All those we're doing were helping us organize which equation they were going into. Now that they're there, you can technically divide off the s cubed from the top, s squared from the next one, s's from the next one, and the constants are just constants at the bottom. I always like doing my math homework. I don't know if it's just because, no, I mean, not just because I turned out to be a math teacher, but, you know, I think it also came down to just liking all of this homework to kind of fit nicely. It was all very organized in my head. Okay, so in here what we're going to say is that we've got an A plus a C plus a D is going to get us 0. That's the first equation. If right, if as cubed plus cs cubed plus ds cubed is equal to 0 s cubed, then the coefficients have to sum up to 0. Okay, well the same thing has to happen for all the other equations. All of our coefficients have to come out to be the values that are over there on the left. So, with A coming out, right, we would be left with negative b plus 3 or 3 minus b times capital A. All right, plus b. It's just one of them. The c is in two places. It's got a let's do plus parentheses negative 4 minus 2b parentheses c plus parentheses 7 minus 2b times d, and that all has to equal 0 when it gets summed up. Okay, next one is going to be a negative 28 minus 3 lowercase b times a plus only one b term plus parentheses. This is b squared plus 8b times our c. And then plus parentheses b squared minus 14b all times d is equal to 0. All right. Thanks for stopping in, Eric. I hope you have a good rest of your day, good rest of your week. We're usually back just Tuesday and Friday doing stuff, but lately I've been trying to ramp up a bit, so I may end up doing a midday stream tomorrow, possibly Breath of the Wild or some math if more people want to come in and ask questions. So, you know, please let me know if anybody is interested in doing some math stuff. I'll be here. All right, we've got then the last equation is going to be 28 lowercase b times a, capital A, minus 28 capital B plus 0c plus 0d. That doesn't seem right. Hang on. Where's the... Oop. Okay, cool. Yep, I dropped it. That's minus 4b c. And minus 4b squared c plus 7b squared capital D equals 1. Alright, still looks really messy, but Kirby. Alright, cool, thank you. And again, thanks for stopping in. See you next time. Okay, so over here, what we're doing now is we've got this coefficient matrix, which then we can multiply by our vector for our variables. And over on the right, what we have is all of the numbers that we get, all the results that we end up with. Now, if you don't know matrix multiplication, believe me, you're going to. What we have here is a 4 equation by 4 variable coefficient matrix, a 4 variable by 1 vector. So this only has 1 column to it, and this ends up getting us a 4 by 1 result. Now, the way matrix multiplication works is you're going to take the first row, multiply it pointwise by the first column, and then first row, first column goes into your result value. When you multiply all of these things together in the first row by the first column, I'll show exactly how that's done, then those things get added together to form that last one there. So if we did like ABCD like this, this would be A times big A plus little b times big B plus little c times big C plus little d times big D is equal to 0 in this case. Right, that's how matrix multiplication works. It works out very nicely, and this is just kind of like a thing that people invented, so may not be like 100% comprehensible to everybody, but at the same time it makes perfect sense if you've done any sort of like matrix theory. Some of you might eventually. Okay, so we want our coefficients. So our coefficients for our first equation are going to be 1a, no b's, 1c, and 1d. This is multiplied by our variable matrix, ABCD. And again, our resultant matrix out of this is 0, 0, 0, 1. That looks like not a 0. All right, 0, 0, 0, 1. Right? So again, here, this is how this one works. We're taking first element with the first element from the first row and the first column. This gets us the result in the first row, first column. Summed up with, So element 1, 1 with here element 1, 1 as well. Here, this is element 1, 2 matched with element 2, 1. Element 1, 3 with element 3, 1. Multiply those. And element 1, 4 with element 4, 1. Multiply those. Once you get those multiplications, once you get those products done, add them all up, and then you get the resultant on the top. So here we see 1a plus 1c plus 1d plus 0 b's is equal to 0. All right, so again, this is where it gets a little weird, because we've got like all this stuff in here. So this is going to be 3 minus little b for a, 1 for capital B, negative 4 minus 2b for the coefficient of c, and 7 minus 2b for the coefficient of d. Coefficient of a for the next line is going to be negative 28 minus 3b. Coefficient of b is 3. That one's nice and easy. Coefficient of c is b squared plus 8b. And coefficient of d is b squared minus 14b. Okay, and last one, 28b, negative 28. Negative 4b squared and 7b squared. Right, and that is the system of equations that we're working with. It is a bit hard, but it is also possible to solve this in terms of b. Might get a little crazy in order to knock out a lot of this stuff. We said for any particular b value, there should, in theory, be these a, b, c, and d values, which would split our fractions into pieces. Or split our main fraction into multiple pieces. Okay. I'm going to preempt our ads by going and getting some water, because I am out of tea and it is getting late. So I probably should not have more tea. Or coffee, because that would make it a lot worse. If anybody does have any questions, again, please feel free to drop that in chat. Or if you have another math question, you can go to the Discord server here. This is The Elements, run by Penn Center, and ask in the math forum section if you need to. If you're on mobile, for instance, I believe if you click the header of what channel you're under, it'll pop up with your options menu, and at the top is threads, and then you can add a new thread. Those of you who are on desktop, it's not a problem. You can just click the start a new thing. Barring that, there's also a problem chat area. And if anybody is unsatisfied with my answers, please keep in mind my goal is to get you to be able to do stuff, not to necessarily just do things for you. So, all right, we'll see you in 3 minutes. I'm going to grab water and maybe a small snack. We'll see how things go. See you in a few minutes. This is Obi-Wan Pez. You're at nSimplex Pachinko, and thank you for sticking around. We'll see you after ad break. Hey everybody, I will be right back. I need to go lock my front door because, you know, it's not locked at the moment. Be another about minute or two. Door locks are very important. Went downstairs and, you know, door's just unlocked. It's fine. Spouse hasn't been there for half hour. That's fine. There's no problem. It's just, you know, could be one. Alright, if anybody does have any questions about mathematics or anything like that, I'm happy to take it. We don't need to continue with this because this is going to be difficult. Oh man, Pen over here just doing everybody's homework. You know, this being said, this might actually be interesting to still do some amount of linear algebra if you've never seen like how to do linear algebra before. So if we were to start with a if we were to start with a system of equations, it's not awful. Ah, 3x3 system of equations word problem. Oh my god, that's from one of my colleagues. That's great. I'm not doing that one, but I know their word problems too well. So alright, this one's easy enough. I mean, obviously it's not that bad, but so if, for instance, you have rent that's being collected from 3 different kinds of apartments, condos, whatever, that are of different sizes. So all of the ones of a particular type are going to be the same, let's just say, and so the problem here is that the total amount of rent that was collected last week was $1,240. Or if you want to, we can do British pounds as well, because I can do the symbol. Dollars is just default in my head, of course. 10% of the small apartment rental amount went to repairs. They're just doing some nice ones here. So 20% of medium apartment rental went to repairs, and 30% of large apartment rental went to repairs. So all these end up being the same. It's just percentage-wise, it's slightly different for each of these sets. Okay. Large apartments. Rent for twice as much as the small ones. And the total repair bill was $276 last week. So, sure. We're going to create a system of equations that reflects this particular setup, and then we want to be able to solve that system of linear equations, because they are just linear equations. Okay, so the total amount of rent that was collected last week was $1,240, given some number of size A apartments plus some number of size B apartments plus some number of size C apartments. The total rent, when you add all this stuff up, is $1,240. When was this thing published? Whose book is this? No. Nah. Okay. So this is saying that 10% of the small apartment rent went to repairs. So this is going to be 0.1 times our A. Yeah, the amount of money that was coming in from the A apartments. Plus 20%, 0.2 from B, plus 0.3, 30% from C, got us to the repair bill of $276. Yeah, seems awful low. All right, and our large was, is, so therefore, right, this is an equivalence relation. This is that. C, the large, is twice as much as the small. Twice as much as the small ones. If you look at it, if you take C just as it is, or if you double A, you should get the same values. Therefore, A is smaller. Right? Makes sense. By a factor of 2. Alright, so with this, we have a system of equations. Now, most algebra students are going to be taught / have learned / do, okay, we're going to take this thing right here, and we're going to substitute it in to the other C variables in the other equations. So in this way, we reduce this from a 3-variable equation to now a 2-variable equation. Okay, 0.3 times 2a is going to be 0.6a plus 0.1a is 0.7a plus 0.2b equals 276. Alright, so we're going to take this one out just for now because that's our work. And if we look at the A and the B above, oh, wait a minute, right, we can actually just bring all this down, never mind. Right, so let's take, take this all down here. We're going to make this its own system of equations. Alright, so a plus 2a is going to be 3a plus 1b is equal to 1240. Okay, so in this particular case, what we would want to do is to look at this and say, you know, what values are we trying to make equivalent in this case? I'd say we'd want to set our b's. You can either do this as substitution because b is nice and by itself, so you just move the 3a over. Or if we want to show the other method, which is not substitution but elimination, this actually ties into matrices much better. So in order to do elimination, we want to say, okay, how many of each equation would we need to either add or subtract from the other in order to knock out one of the variables? Well, our b's are in a relationship of 1 to 5, or 5 to 1 is what they are. So if we were to say how many do we need in order to make them equivalent, we would need a 1 to 5 ratio. So let's take this as, we can multiply this one by 1 and this one by 5. And we want to make sure that one of these is going to end up being negative. So that we can just add straight down when we get to it. Yeah, okay. No, we're good. I was worried for a second. Okay, so going across, this is going to be just standard 3a plus b equals 1240. And on the next one, negative 5 times 0.7 is negative 3.5a minus negative 5 times 0.2b is going to be a negative b is equal to negative 5 times 276. So 200 is going to be times 5 is 1,000, and we're in the negative now. Okay, 5 times 70 is 350, so 1350, and then 6 times 5 is going to be 30, so that's going to change the 50 to an 80 here. So negative 1380. Then, when we just take our equations and we add them, all of our a's, b's, the equality sign, and the constants are in the same locations. So we can just add straight down. This is going to get us a negative 0.5a plus 0 is equal to a negative 1380 plus 1240 is a negative 140. And then we can divide by negative 0.5, or it's a negative 1/2, so multiply by negative 2. When you multiply by negative 2, a is going to be negative, no, a is going to be positive 280. What decade was this written in? I don't think you can get a studio apartment anywhere for $280. Yeah, these questions need to be updated. Whew. We also know that 2a is equal to c. So twice 280 is going to be 560. And then from all of our equations that we've had so far, I guess the 3a plus b equals 1240 is going to be the easiest way to get this. I might even go all the way back to the beginning and say a plus b plus c was equal to 1240. So 280 plus b plus 560 equals 1240. We already know that this was 840 plus b, right? 3 times our initial 280 there. 1240. Subtract 840 from both sides. This is the same as adding two equations together, which we just literally did right up there. So add our two equations together. 840 plus b equals 1240. And negative 840 equals negative 840. Add your two equations together. We end up with b is equal to 400. So the small ones cost $2.80 per week. There we go. Medium apartments are $400 a week, and large are going to be $560 a week. Okay, if anybody has any questions, let me know. Otherwise, we're going to do this again, but this time we're going to do it in using matrix algebra. So here, we said that a plus b plus c is going to get us 1240. So here, again, first row multiplied by the first column. So we take the first element of each, multiply them together, that's a. The second element of each, that's b. And the third element of each, that's c. Multiply them together, and then add all those totals up, the subtotals. So we get 1a plus 1b plus 1c is equal to 1240. A plus b plus c equals 1240. It's what we started with. Second set, we had 0.1a plus 0.2b plus 0.3c was equal to 276, I believe. Yes. And lastly, this one takes a, half second to think about, but c is equal to 2a. Well, we've got all of our a's, b's, and c's on one side, so shift it. This is going to get us a negative 2a plus c is equal to 0. Can't see that. Right. So with that, that's going to be a negative 2a plus 0b plus 1c is going to get us 0. So using these items, we need to make sure that we get what we want to get. Is that 1a, no b's and no c's, is going to get us a number, right? Whatever it is. No a's, 1b, and no c's is going to get us another number. And no a's, no b's, but a c is going to get us a third number. Again, we already know what it is. It's 280, 400, 540. I think, right? 560. So we already know what the answers are. It's just that we need to figure out how to get that. Well, good news. All of this matrix algebra stuff is basically just a giant elimination game. So here we're saying that we want to take each of the rows and do something with them using standard elimination tactics in order to move closer to the identity matrix, which we saw on the left up above, the 1 0 0 0 1 0 0 0 1 3x3 identity matrix. So what I'd like to do here is say, okay, if we just left row 1 where it is, don't do anything with it, it's fine. really what we're looking at is I want to keep this 1 at the top left corner. That's good. I like that. Now we need to change all the rows below. The easiest one to do is our third equation. So if we take our third row and then we add 2 of the first row, we're going to eliminate that first variable in that third position on the third row. So we want this gone. That's how we ensure that we're going to get rid of it. And same thing for row 2. We take row 2, and in fact, let's take 10 times row 2, and then subtract row 1 from it. Okay, so we didn't change the first one. It's 1, 1, 1. Times that is going to be equal to 1240. Didn't change the first one at all. Second one, we've got 10 times row 2. So 10 times 0.1 is 1 minus the 1 up above it. Just like we engineered it to happen, it's going to get us a 0. 10 times 0.2 is going to be 2 minus 1 is just going to be 1. And again, I like that because now we've got 2 items that are in the place that we want, and we've got the 0 in front of it. That's nice. Okay, and again, 0.3 times 10 is 3, minus 1 from above is going to be 2. So 1, 1, 1, 0, 1, 2. It's looking more like the identity matrix up above. Looking pretty good. Okay. So we go to the third row, and we said, okay, we're taking our third row. Oh, wait, no. We got the number on the other side, too. So 10 times row 2 is going to be 2,760. Minus row 1 of 1,240 is going to be 1,520. Okay, third row. Take what's in row 3 and add 2 of row 1 to it. That's going to get us a 0. Row 3 is 0. Now add 2 of row 1. That's going to get us a 2 in that position. And then row 3 is a 1 plus 2 of the thing up above it is a 3. Okay. Yeah, 2 of row 1. Then we're going to do the same thing with our constants. So we have a 0 plus 2 of row 1. So this is going to be 2,480. All right, now we just do it again. So we need to get rid of this 2 that's here. And again, we can take row 3 and then just subtract twice row 2. Or if we don't want to deal with negatives, we can kind of flip that around a bit and make that row 3 is going to be negative and row 2 is going to be positive. All right, in addition, we can also keep this 1 here, but then get rid of this 1 here in the first row, second column. So if we add, subtract, I guess. Take row 1 and subtract row 2 from it. We're going to end up with negatives in this case. It's all right, I guess. There's a reason. Okay, so row 1 minus row 2 is going to be 1 minus 0 is 1. Next one, 1 minus 1 is 0. Next one, 1 minus 2 is going to get us negative 1. There's also another helpful thing that we do sometimes. This is called augmenting the matrix. We just put a dotted line there, which means, okay, look, this matrix is going to be continued over here. We already know what's going to be in this middle stuff. It's just the variables, and then we have an equality sign. So we just got to remember at the end to shift it back. This was 1240 minus 1520 is going to be 280. And in the negative direction. Okay, our second row we didn't touch. So 0, 1, 2, 15, 20. Our third row, we said we're going to take the negative of that third row. Might have been a bad idea. It's fine. Works out in the end. And add twice of row 2. So again, here we've got our 2, negative 2, plus twice 1 above it is going to be 2, so that's 0. We had a 0 in the first position anyway. And in the third position, we get a negative 3 plus twice 2 is 4, so that's going to be a 1. Negative 2480 plus twice 1520 is 3040. 3040 minus 2480 is 580. Alright, so we know that that's true from what we saw earlier. Now we're just going to use matrix row operations to clean up the rest. So take row 1, add row 3. Take row 2 and subtract twice row 3. And leave row 3 as it is. So we end up with row 1 plus row 3 is 1, 0, 0. Either dotted or solid, I guess. Yeah, we've done solid before. Row 1 and row 3 is negative 280 plus 580 is going to be 300. What did I do? Nope, that's wrong. Hang on. Let's go back a step. I did some stuff in my head. Yep, 3040 from 2480. There we go. Hey, flex cheeks. So this is regular 3x3 systems of equations, but we're doing it from a linear algebra perspective. So if you've ever done matrices before, we're using matrices and what are called row operations to be able to figure out what the solution to the 3x3 system of equation is. Granted, right, if you already know how to do it by the algebra method, why would you do it by linear algebra? The answer is it becomes a lot faster. When you get sufficiently complicated equations, it's going to be a lot easier to use linear algebra methods than it is to use standard algebraic methods. The other answer is that when you start going out to like, you know, 34 equations with 34 total variables, and yes, that does kind of happen, then you just want to plug this into a computer. And like, how does that work? Well, if you know how to work the algebra, if you know how to program the computer to do it, or if you know the right functions to use, then it becomes a breeze. That is not 580, that is 5. Is it 40? Hang on. 30, 40, minus, okay, minus 80 gets us 560. Okay, good. Just wanted to make sure. Again, we know what the right answer is. It's right over there. But we just want to make sure. Yes. I have taught everything from basic algebra all the way through differential equations for 15 years. Not literally every single semester, but, you know, some of those classes every single semester. My particular specialty is pre-calculus, specifically trigonometry. We do a functions and trig class at my old college. Used to teach at a 2-year college in the eastern U.S. Now we're living in England. Well, Cheeks, feel free. To speak with any and all of these people. They will certainly, including myself, be streaming at least once over the next 6 days. With many of us, potentially multiple times. Okay, there we go. Row 1 plus row 3 is going to be 560 minus 280. Now we can say, yeah, that's half of it. So there's our 280 coming back. Good. We got our 560 down at the bottom with 0 and 0 in those two locations. And if you have any specific questions, let me know. I definitely can do like functions in general. I don't know exactly how deep you want this to go into, but given that it's only a week away, but I do love teaching just all of the deeper meanings behind things so that you understand really like what things mean and not just like trying to memorize facts, because memorizing facts makes you think that this stuff is arbitrary and doesn't really matter. So I want to avoid that as much as possible. Alright, so if we subtract out 2 of row 3, right, from row 2, we're going to get a 0 here. And then if we take 1520 minus 2 of 560, that's going to be 1120 off of 1520 is going to be straight 400. Nice. All right, so in this case, we've got our 1a plus 0b plus, 1a plus 0b plus 0c gets us 280. 0a's, 1b, and 0c's gets us 400. 0a's plus 0b's plus 1c gets us 560. And if we look at that with our answer that we had back over here, a was $280, B was $400, and C was $560. Also notice where we are relative to where we needed to be over here to solve the problem. Right? Maybe I wrote slightly bigger over here, but in matrix form, we can actually solve this faster because we're able to use this elimination method in solving systems of equations to knock these out. Yep. I absolutely hated just being like, okay, memorize the formula, and I rebelled in one of my first couple of like semesters teaching, just like, no, that's not how I'm doing it. And you know, my boss at the time was like, I mean, you're probably not gonna do really well if you don't do this, and I'm like, I don't care. So we had a bit of a difference of opinion. Didn't go terribly well. Ended up leaving that job. But found the community college where I was working and like did the exact same lesson that I did at my public school job for the people at the community college, and they were like, we love it, when can you start? I was like Hey Nap, how's it going? Yep, sorry to hear about that. Our day here was sunny and barely into the 70s, I think. Okay. Okay. So with this particular setup, if you can see where this is going, if you could see where, like, the pattern exists in this, this actually becomes way easier than a lot of the other types of problems that you have. So in this particular case, we're just looking at, like, right, find the equations of these particular functions. So the one on the left is fairly basic, and yeah, just looking at it, you could be like, well, I know that these are powers of 2, so therefore it's going to be this. And you throw it out there. Like, sure, that's fine. It works. I would prefer to look at this as what is my delta x? And what is my r? Which is going to be the ratio of successive y values. All right, this is a hallmark of exponential functions. I actually found this out when I was in, I think, probably 6th grade. We didn't do algebra back then. Our first exposure, possible exposure to like an actual algebra classroom was 8th grade. So our teacher was doing, you know, this this thing, which was find the patterns. And so it was just stuff like this. Oop, hang on. me see if I can actually do this right. Oh, Nah, that's not. No, it's fine. Okay, so it was a problem like this. And then one like this. I remember looking at all of these, and I could figure out the pattern of the first one, right? No problem at all. Okay, this is going to be over here. We're just adding 4 every time. I sure hope I did that right. It'd be terribly embarrassing. And then over here on the left, we're just consistently adding 1 every time. So if we're just adding 1 every time on the left-hand side, and on the right-hand side we're adding 4, then this last one should be 31. Alright, no problem. Good. And this one over here was, again, we're adding 2, but that's the same all the way down here for all of our x's. I think there was one at some point that was like, you know, what's 12 as a secondary answer here. So you'd have to like skip a few before you actually get to it. I remember looking at this and going, well, I can't quite do the same thing as I did before, because here, right, to go from -20 to -17, I have to add 3. And to go from -17 to -10, I have to add 7. And then to go from -10 to 1, I have to add 11. Hey, wait, I've seen this pattern before. And wouldn't you know it, all this stuff was just all that stuff, right? It is the outputs of the previous function that are now going to be my rates of change between these individual values, as long as, again, I didn't mess this up. All right, 19. Yeah. And 23. Yeah. Okay, so that means that the next one down should be plus 27, which should get us a 5065. And then here, this is plus 8, which meant that I went 2 and 2 and 2 and 2. So I should have done this addition 4 more times. So that would have been right, plus 31, plus 35, plus 39, plus 43. So then I have to add all those up and then shift in. Start with 65, add 31 is going to be 96, 131, 41, 70, 213. Right, so to add up all these numbers in that appropriate way to end up with here 4 matches with 65 and 12 matches with 213, like, that was kind of neat, right? So again, this is me in 6th grade. It wasn't quite this hard, but oh, I get it. It's finding a pattern and then making it work. And then on this one, I tried to do the same thing. On the left side, I got all of my delta x's were 1 again, all of our changes in x's. all of our delta y's, our change in y's, were plus 1, plus 2, plus 4, plus 8, plus 16. So at least I knew that this was going to be plus 32. However, I was also like, wait. Those are just the same numbers as those. Which means that if I go another layer deep on this and say, okay, I'm going to get plus 1, plus 2, plus 4, plus 8, plus 16, again, and again, and again. So no matter how many times I try to find the rates of change of this particular set of functions, right, I can't do it. I'm just going to get the exact same numbers that I had on the previous round. They're just shifted down slightly because they're in a different position. Okay, so the ones on the left here we know are linear functions. The one in the middle, it turns out, is a quadratic. And the one on the right is an exponential. The differences here are that the linear function is additive. The quadratic one has an additive rate of change. And the exponential one is not additive at all. So instead, in order to say we're doing the same thing from one line to the next, to the next, to the next, what we have to say is, oh, well, we're taking every individual value and we're multiplying it. So I'm taking my 1, I multiply it by 2, and I get 2. I multiply that 2 by 4, and, that 2 by 2, and I get 4. I multiply the 4 by 2, and I get 8. By 2 again is 16. By 2 again is 32. By 2 again is 64. So exponential functions are a multiplicative pattern rather than an additive pattern like linear, and the quadratic has an additive rate of change. So looking at all of this, we have to say, okay, our exponentials are going to have to be a little bit different. We do know that the easy one, right, the original way back here, this one's nice and easy, right? We have how many 2's are being multiplied together. There is 1, 2, therefore the output is 2. If we don't have any, right, either you could say, well, we don't have any multiplicative values. So when we strip away all multiplicative values, a 1 is left over. Or we could start down here and say, we've started at 16. How do we go back further up the chart? Well, in order to go up, we have to divide by 2 every single time. Right, whereas going down, we're multiplying by 2 every time. Taking the previous value and multiplying by 2 every time, not the x values, right? So how does the x value then determine the y value for this one? Again, fairly easy. We're just saying, okay, y is going to be equal to 2 raised to the xth power. So 2 to the 0th power is 1, 2 to the 1st is 2, 2 to the 2nd is 4, 2 to the 3 is 8, 2 to the 4 is 16. Because that means we're doing 2 times 2 times 2 times 2, which is 4 times 4, which is 16. Okay, this one is going to be significantly harder, but there is a specific way that I've been training my students for quite a while. And that is to look at the individual distances that this is away from something and see if there's some sort of recognizable pattern. So in this particular case, sure, everything's multiplied by a third from a whole value. Okay, we can deal with that later. One of the other options is to look at the actual values that we have here. Right, we have a... Should have moved that a bit. Yeah, there we go. Okay. So from here, what we do is we mark out where these points are. So -4 by 5/3 is 1 2/3. It's about here. -3 is -4/3, so 1 1/3 here. -2 2/3 is right about here. This isn't very good. They look too linear, but I have a suspicion this one's a bit higher. -1 2/3 is going to be here. 0 by -10/3 is going to be here. And 1 by 26/3 is 1 2/3. So we're down here. Looking at the original, again, not difficult, but it's not very evenly spaced. That's much better. Alright, let's make that 16, which means that halfway is going to be 8, halfway of that's going to be 4, and halfway of that's going to be 2, and halfway of that's going to be 1. Okay, we've got 0 1, 1 2, 2 4, 3 8, and 4 16. And then we've got on the other side, because we don't actually show that on this set, but if we divide by 2 over and over again, we've got -1 by a half, -2 by a quarter, -3 by an eighth, -4 by a 16th, etc. This is going to be true for all of these exponential functions, no matter what they are. So these behaviors are really what we want to focus on. We have an initial value at 0 1. Now if you mess with the equation, y equals 2 to the x, in very specific ways, it's going to do very specific things. So again, my students have been taught this at the beginning of the semester, and it takes them about 0.2 seconds to catch on that we're doing the exact same thing for this one that we did for all the other functions that we talked about. All right, now the important thing is, for this particular function, all of our y values were doubling every time that we went and increased our x by 1. Increasing our x by 1 just means we're moving to the right one space. So if we move to the right one space, we double our y value, which is the y distance, which is the height, at least for this function. Right, that distance here is 1, which doubled the distance that we started with down here. On the next one, we've got a distance of 2, and we're doubling the distance again. On the next one, we've got a distance of 4, and we're doubling it. On the next one, we're doubling it again. So, this is our scheme that we're going to use for this particular exponential function. Move right 1, double the y height. What are we measuring from, though? Right? What do I mean by height? Well, we're measuring from the y or the x-axis. And so when we measure from the x-axis, we're always doubling that height every single time we move right one space. Okay, what if we move left? If we're going to move left instead, we're going to halve the y height, chop it in half every single time that we move 1 to the left. Again, it's just part of the scheme of this particular thing. So what about this one? Right? I don't necessarily see any particular value that it's headed towards, but you can kind of guess a couple if you want. Or in fact, you can check distances between points. So what's the distance between, let's say, this one and that one? Well, this is a negative 2/3 for our y value, right? Negative 1 comma negative 2/3. And then this one here, right? Oops, hang on, back up. Right, this one here is 0 comma, this was 1, 2, 3, and 1/3, or negative 10/3. How far are those apart? Right, the distance there is 8/3, so therefore, if this has a scale factor of 2, which we can check again, what about this one here, right? This was negative 26 third, 1 comma, negative 26/3. The vertical distance between these 2 points is it's in the negative direction, so we might as well do that. But this is going down 16/3. Okay, it was going down 8/3. Now it's going down 16/3. Great, we've just doubled the distance So therefore, we know that we can go a negative 8/3 up as well and find out where that other point is. So if we take negative 2/3 and add 8/3 to it, we're going to get to positive 6/3 or 2. Now on the original, it was the x-axis. And as we move further and further to the left, we kept cutting our distance to the x-axis in half over and over and over again. This will always have some distance between it, the point you have, and the x-axis. There's always a distance. You're just cutting that distance in half every time. But there's still some space. So therefore, we never reach, in this case, y equals 0. We never get there. This is what's called asymptotic. Right? It's asymptotic behavior because it gets closer and closer and closer, but never actually makes it. It's just forever getting closer. Right? Y equals 0 is the equation of the asymptote. And again, the behavior is asymptotic. Well, that is a fundamental fact, again, for all exponential functions. We're going to say, okay, we're measuring our distances from y equals 2. So if we go further over this way, all these distances are just going to get cut in half and half and half again. So negative 8/3 over here for this one, that distance becomes a negative 4/3, and then a negative 2/3, and then a negative 1/3. The distances are what I focus on. So I keep trying to tell everybody, don't worry about the specific numbers that you get every single time, because they're always all going to be different. What the pattern is here is that the distances between these points has to be the same pattern that we had in the original. So we had our parent function. This one is going to be our transformed function. And I guarantee you, right, it's still going to have a 2 with an x in the exponent. There's going to be some changes, but it's going to have those, definitely, 100%, because it follows the same pattern-ish, right? We know that it's going to take the same basic pattern to make this thing as it did for the parent function. Right? So the scheme is we're doubling our distance from the asymptote to whatever point we're at every single time we move to the right one. Okay, so I can actually choose anywhere along this entire thing to choose my initial point. Doesn't matter which one you do. Now, I do tend to like easier stuff, so, you know, going with the 1/3 here or going with the 10/3 here spares us from doing some of the transformations a little bit more difficultly. But if I choose, let's do this one, negative 8/3 as my initial point. Nope, sorry. Our distance here, the initial distance is going to be negative 4/3. So I'm going to say that that initial distance is going to be my multiplier that is out front of this function. This is what's called a vertical scale factor. So it's going to stretch our original parent function, y equals 2 to the x, by a factor of negative, flips it under the asymptote, 4/3. Right? Changes our initial distance from positive 1 to negative 4/3. Okay, and then we do 2 to the x somewhere in there. All right, the x compression value is going to tell us, like, how often do we double? Okay, well, we double our distance every time we move to the right one. So it's the same as 2 to the x. Our b value is just 1. We're not messing with it. Our c value is telling us how far have we moved to either side in order to get our initial point. Now again, I said you could choose this as your initial point, in which case your c value is going to be 0. You don't shift at all if you choose this one. We instead chose this one. Chose this one mostly just for its a value, and I can also, yeah, we can, to also show you that we can use this c value. I'll show you the letters in a second here. So this is telling us that we're at an x value of -2 where we have our initial value. Our initial value in the original parent function, y equals 2 to the x, was at 0. X equals 0. And y equals 1. So, like, how far do we need to change our value? We're currently at -2, so that means that we have essentially started from this value of -2, and now we're pretending that it's 2 bigger than it actually is at 0. So we need to add 2 to our x value in order to make it the initial value. This has the effect of taking this value that was here and shifting it left 2 spaces. Okay, and d, there's an additive value on the outside. Normally, our functions are asymptotic to the x-axis, so y equals 0. But in this case, we're asymptotic to y equals 2. As we start getting closer and closer and closer to negative infinity, right, 2 raised to a negative power is going to make a smaller and smaller and smaller number. So then this whole term, 2 to the something, effectively becomes nothing. So where are we? Well, we should be at y equals 2. When x gets really, really big in the negative direction, that whole term gets wiped out, or very nearly wiped out. And so what's left? Literally y equals 2. Something that's close to 0 plus 2. So this is our equation. Or rather, this is one of the forms that our equation could take. Because instead, if I choose my initial value as this one, right, 0, -10/3, then I could say, okay, this is going to be y equals, this is a -10/3 times 2 raised to the x. We didn't shift left or right, so it's just 2 to the x. And then plus 2 on the outside, because again, we shifted up 2. If you plug these in, you're going to get the exact same thing. What about this one? What about like one in between? Sure, we could do that. It's going to be a pain in the rear. I don't want to do it. Let's do this one. At 1, -26/3. Okay. Oh, you know what? I messed up. It's not the value -10/3. That's there. It's not negative 10 thirds, because that's our location. What's our distance? That's what needs to be said there, right? What is the distance that we are at this location? That is 8 down and 8 again thirds, so negative 16 thirds. Y equals negative 16 thirds times 2 to the x plus 2. Okay, how about the next one? That's, again, 1 comma negative 26 thirds. The distance is going to be negative 32 thirds. So y equals negative 32 thirds times 2 to the x. In this case, we are shifting now to the right. So we are now pretending that our initial value of 0 needs to be smaller than it currently is at 1. X equals 1. Right? What if we move this back to 0? What would that do for us? Well, it's going to subtract 1 from our exponent. All right, and then plus 2 again, because our asymptote isn't changing. What's changing? It's the scale factor. Our A value that's sitting out front, the negative 4 thirds, or the negative 16 thirds, or the negative 32 thirds. How did it change? We took a 2 from the exponential thing, and we multiplied it not into the 2, but now into the A value out front. So if we take, another way to do this is to say, okay, if we took y equals negative 4 thirds times 2 to the x plus 2 is the same as 2 to the x times 2 to the second. And then this is y equals negative 4 thirds times 2 squared is 4 times 2 to the x plus 2. What is that? That's y equals negative 16 over 3 times 2 to the x plus 2. Oh, look at that. That's the same thing. Whether you do it algebraically, or you do it graphically, or you analyze all the different distances and things like that that are going on here, whichever way you're going with it, right, you should corroborate your evidence through multiple different channels. So you look at all the different ways that we got the exact same equation. That's what's important for us. All right. If anybody has any further questions, please let me know. Otherwise, we're going to head over and see one of our other friends. I gotta figure out who's on. That's gonna matter. Hey, Dawn does math, in fact. We also have actual education. Dr. Gold is live doing math. Tonight we have Penn Center, who is doing Majora's Mask. Astro Canuck is doing, well, it says makers and crafting, so it must be Legos. Rock It Sage is talking about volcanism and talking about some, yeah, talking about some cool stuff there. Danny Highway is live and doing allegedly Ocarina of Time, with Penn doing Majora's Mask. Not sure exactly how that works. They said they were doing a randomizer, so I thought they were doing the same thing. Let's see. Anyway, we're gonna go over to... yeah, we'll go over to Dawn. Oop. Yeah, we'll go over to Don's. And I don't know how much longer he's going to be live, but he's probably also going to go over to somebody else doing math. So anyway, I hope you all have a good night. I will likely be in tomorrow at some point to do maybe a, oh wait, no, we're getting our stuff, never mind. I will not be in tomorrow because I will be getting my stuff. So hope you all have a good night. I will see you probably on either tomorrow night or Thursday to do some extra stuff and celebrate the fact that I have my chair and my desk instead of sitting on the floor. But anyway, I hope you all have a good time. I'll see you tomorrow, the next day, something, and we'll do some math, we'll do some games. Have a good night. My name is Obi-Wan Pez. This is N Simplex Pachinko. See you later.